Alright, welcome everyone for joining my talk. My name is Junwei. So today I would like to present my paper to you. My research topic is about social network security, and the title of my paper is Efficient Privacy Preserving Users Matchings with Intel SGX. So here is the outline of my presentations. I will begin by introducing the background of my topics, then I will discuss our system designs and protocols. Finally, I will present the performance analysis and conclusions. So when we talk about social networks, people will think of social interactions, meeting new people and having a virtual communities with friends. As the name social networks imposes, the most fundamental features that a social network should provide is to make new friends. We refer this as users matchings. Features such as friend recommendations are based on users matchings, which is done by computing the similarities of multiple profiles to find out if there's a match. While such features facilitates the process of making new friends, it poses security issues as many companies did not handle security properly, which causes data breaches and puts the privacy of their users at risk. On top of that, with the prevalence of cloud computing, companies outsource computational power to cloud providers, and as a result, all sensitive information is exposed to the cloud providers, which also causes security problems if a malicious administrator decided to steal the data without authorizations. So, as the consequences of data breaches would most likely result in a lawsuit, in a financial loss, and in some cases legal actions from their users such as lawsuit will file against the company, it becomes obvious that a solution is needed for addressing the problems. So far, many solutions have been proposed to address the problems. One obvious solution is to utilize encryptions, which in this case is to encrypt the user's data. While it solves the problem of securing the data, it becomes challenging to processes, as this is because most algorithms are not capable of analyzing encrypted data. As the result, features such as friend recommendations are no longer feasible, and later oblivious transfer is used for secure comparisons of the users, but it is limited in functionality as oblivious transfer is only capable of binary comparisons. Recently, researchers have introduced homomorphic encryptions to enable secure computations. However, it is slow and only simple mathematical operations can be done. So given the limitation of those previous works, we attempt to overcome the problem of secure computations by utilizing trusted execution environment with Intel SGX. By using TEE, we can address the problem as TEE offers a virtual black box with strong security guarantees, and no one can access to the contents running inside without additional computational overheads like homomorphic encryptions did. On top of that, to facilitate the limitation imposed by XGS, such as side channel leakage, other techniques such as searchable encryptions and oblivious spams are employed to strengthen the security. So now let's talk about our system designs and contributions. There are three components in our models. Users, an untrusted server, and secure enclave that coexists in the server and is created using Intel SGX. Each user will have a unique secret key that is known to the users and the secure enclave. The untrusted server is responsible for storage such as encrypted profiles and matching tables, which we will discuss shortly. Inside the secure enclave, we have a key table, index map, and the master key that never leaves the enclave. So to start with, we first give an overview as to how the protocol works. Each user will have a profile that describes the user's preferences such as gender, age, interests, and so on. Each attribute is encrypted with user's secret key before it sends to the secure enclave via secure communication channel. Upon receiving the encrypted profiles, the secure enclave decrypts the profile and constructs a search table based on the searchable encryptions. which involves computing a search token and secret pair for every attribute. Finally, secure enclave returns all search token, secret pairs, and the encrypted profile to untrusted server for storage. And when a request for a user's matching is made to the enclave, the secure enclave computes the search token and fetch data related to the search token from the untrusted server. And it computes the similarity scores to find candidates for the matching request. So next we will introduce how the search table is constructed in a little bit more details. So to put it simply, the idea of searchable encryptions is to attach a label for the data that needs to be searched, which is like an inverted index that works as a key-value mapping relations. In this case, we use the attribute as the index, followed by a list of encrypted users' ID that contains these attributes. In other words, let's assume that someone is interested in programming and the attribute of programming in this case acts as a search token, followed by the ID of that user who is interested in programming. The search token for this attribute is computed as follows. The attribute is joined with the master key of the secure enclave, digested using a deterministic function such as SHA-256 or so. The result of the deterministic function is used as a search token. Then next we have a secret pair. The secret pair is the key value pair that stores in the matching table inside the untrusted server. And to prevent the collections, an index map is used to mitigate the issue as we don't want to accidentally overwrite the data stored in the untrusted server. We get a counter from the map using the search token, and if a counter is not found, we create one and assign a 0 to it. Next, the search token is divided into two parts for computing the secret pairs. The first part of the token is joined with the counter that we mentioned, and the second part of the token is used as the key to encrypt the user's ID. The secure enclave repeats the process until all attributes are handled properly and send it back to the untrusted server for storage. So now let's talk about searching. Searching is quite simple to follow once we understood how the construction of the table works. Users send an attribute indicating the type of people she wants to know about, encrypts it and sends it to the secure enclave. Upon receiving all requests, it computes the search token using a deterministic function and the master key. The search token is then sent to the untrusted server and follow the same pattern as well. Except for the counter, which in this case is set to 0, as the server never knows for sure how many users will have the same attributes. So the server needs to perform a linear search by incrementing the counter to generate a key and query the table to see if there's a match. For all matching results, it decrypts the value in the pair using the second half of the search tokens and query the profile according to the decrypted results, which is the user's ID. At these points, profiles are sent back to the secure enclave, which can be decrypted and processed for computing similarity scores. So far we have discussed about the matching protocol. From now I will begin to talk about the security precautions that we make to strengthen the securities. As some of you might already know that Intel SGX has suffered from so-called side channel attacks, which can leak a significant amount of data to the attackers. Among all side channel attacks, we are interested in timing attacks. So timing attacks works by measuring the amount of time required for the processors to access some data, and based on the mapping relations between the memory and the cache, and the timing which indicates whether a particular block of data has been fetched into the CPU's cache, the attacker can guess what program is doing based on these informations. Attacks such as Spectrum and Meltdown are all timing attacks with the help of speculated executions. And so the searchable encryptions that we adopt did not come with special treatment to handle timing attacks. Therefore, we adopt ORAM techniques for the index map that stores within the enclave. So ORAM works by obfuscating the timing channel in a way that one cannot distinguish the real target. Among all ORAM solutions, we use Path ORAM for its better performance. In short, Path ORAM is a binary tree structure where the path describes the route between a root node and one of the leaf nodes, and the data is randomly stored at the nodes within the path. As the name obliviousness infers, the entire path is read or written accordingly to ensure the timing is consistent. Moreover, we also use the same idea to resolve memory uses that comes with Intel SGX, as it only has around 90 megabytes of usable RAM for the developers. It is crucial to avoid paginations as it occurs a huge delay. To do that, we apply the ORAM to the key table with additional encryption so that it can be saved to store in unprotected memories, and only fetch the data if necessary to avoid paginations, at the expense of extra communication overhead. Next, I will talk about the performance. So we implemented the protocol. We implemented our matching protocol in a Dell laptop with Intel SGX support. In the end, two variations are born. Vanilla implementations did not utilize ORAM to prevent paginations, whereas the extended versions did that at the expense of extra communication round between the untrusted server and enclave. So first, we present the memory uses for the matching table in untrusted server. We run 3 experiments to measure the total RAM consumptions, with each round containing 5, 10, and 15 attributes for every dummy profile we generated for measuring RAM usage. The worst case scenario we've observed is that it takes around 1 GB of RAM to hold 2 million of profiles, with each of them having 15 attributes. As there is no limitations in RAM usage in untrusted server, we pay our attention to the RAM usage within the secure enclave. The memory footprint between two variants is significant. We observe that the extended version uses significantly less amount of RAM thanks to the ORAM that securely outsources the key table into untrusted memory with protections. Whereas the vanilla implementation triggers pagination with around 2 million records in protected RAMs. The smaller footprint from extended implementation also comes with the cost of an extra communication round, which we will discuss right now. The last experiment is to see how quickly can both implementations respond to a matching request. We set up 3 environments with each of them containing 100K, 500K, and 1 million records in the matching tables. We set the numbers of returned users from 25, 50 to hundreds. That means that the end user will only get numbers of users in return. And we will observe that the vanilla implementation is the quickest, as the key table is stored in the protected memory and did not require an extra communication round to fetch the key. Whereas the extended implementations can be up to 5 times slower, but with the benefits of smaller memory footprint. We also compare our work against the most recent work in users matchings that utilize homomorphic encryptions, as the existing works utilize homomorphic encryptions with multiple parties. Our protocol outperforms that work and also provides a strong security for the user started. So in conclusions, we propose a users matching protocol with Intel SGX, and we employ searchable encryptions for quick index and ORAMs for mitigating timing attacks against critical components such as index maps and key tables. We avoid the issue with paginations by introducing 2 variants to show the performance differences, and we compare our work with the most recent one, and our results shows that it has gained performance improvements. So this is the end of my talks, and thank you for your time and participations. And just If you have any questions, please feel free to send me an email to discuss, and I'm happy to answer questions from any of you. All right, thank you.